In part 2, we discussed the elements that make up semiconductors. We said we've got silicon and germanium, and we add elements from column 3, boron, aluminium, gallium, indium, or elements from column 5, phosphorus, arsenic, antimony, and bismuth. We add those to our silicon or our germanium in order to create our p-type or our n-type materials. When I'm adding elements from column 3 and column 5 to silicon and germanium, that process is called doping. The elements from column 3 and column 5 are called impurities that gets added to the silicon or the germanium. Now, the ratio at which doping takes place is very important for the specific type of semiconductor. Depending on the ratio of doping, we allow the semiconductor to gain different application possibilities. In part 2, we looked at the diode. In this part, we're looking at the Zener Diode. When it comes to the construction of the Zener Diode, again, we've got our n-type material and we are combining it with our p-type material in order to form a p-n junction and our depletion region in the middle. The difference, however, with the Zener Diode is the doping levels of my n and p-type material is different to that of my normal diode. That will result in special characteristics which we'll look at in a moment. So when we've got our p-n junction that forms up our Zener Diode, when we connect it in forward biased, we will see that it responds exactly the same as a normal diode would. I get a small leakage current at low voltages, and then as my voltage increases, once it reaches 0.6 volts or 0.7 volts, that 0.6 or 0.7 value will depend on which actual Zener diode we're using, but typically around 0.6 volts we will gain forward conduction in connection with this series resistance and applied voltage. In the reverse state, however, we gain again that small reverse voltage or that small leakage current, however, once it reaches a certain level, remember, forward biased says we've got, let's color code these, forward bias says we've got positive on the P, negative on the N, depletion region will decrease, and that will allow for current to flow once we reach 0.6 volts. In reverse bias, the p-n junction or the Zener diode responds differently. So if I've got a positive and a negative connected in order to reverse bias my depletion region, what happens is that depletion region increases, but because of the light doping of the Zener diode, that depletion region increases very quickly in connection with the size of the applied voltage. So when that voltage increases, eventually it's going to take over the entire p-n junction, all the n-type and all the p-type material, and that will allow for current to flow through in the reverse direction. Now, depending on the doping levels and the doping ratios of the n and the p-type material, that voltage can be controlled at a certain level. Now additionally, when we get that breakthrough voltage, when we get to that reverse breakthrough level, reverse breakthrough, we find with the Zener diode that the voltage there will remain constant. So if I increase the reverse polarity up to, let's say that's 5 volts. So I'm increasing that voltage in reverse direction, and when it reaches 5 volts, conduction takes place, or the depletion region takes over the entire component and conduction takes place. Now even if I increase the voltage further across the Zener diode, that voltage on the Zener diode will always remain constant at that breakthrough level. Because this breakthrough happens at smaller voltages, the Zener diode does not burn out when it experiences the reverse current flow as a normal diode would. Now the issue with the Zener diode, let's just quickly draw the circuit symbols. The symbols are very similar to the normal diode, except the Zener diode has that zigzag, or the Z, on the cathode. Remember, the arrow indicates where the N-type material is, and the N-type material is called my cathode, so that will be my anode. So in forward bias, we will have a positive on the anode and a negative on the cathode. That's supposed to be green. Positive versus negative there. In the reverse direction, we will have our Zener diode, and we will have a negative on the anode and a positive on the cathode. The Zener diode is specifically designed to operate in reverse bias so that it can serve as a voltage regulator. Now, in order for us to ensure that Kirchhoff's law isn't broken and to protect the Zener diode from situations where we have excessive current flow through it, the Zener diode is always connected in series with a resistor. That resistor connects in series with my Zener diode, and when I supply a voltage, let's accept that the voltage I am supplying over here is like that, my Zener diode will have a set voltage, let's say at that level. So what happens is the Zener diode will generate a constant voltage across itself that serves as my output over there, and then the remainder of the voltage that I apply to the circuit will then be seen on my resistor